Uh, thank thank you. Let me start writing. Okay, so thank you very much. It's first of all, it's great to see all the friends and familiar faces together, and also it's an honor to get invited to give a talk on this seminar. And of course, big thank you to Soso for organizing it. Uh, right. So this is all joint with Piotr Strongowski in Harvard. He's a postdoc in Harvard, and this project was a joint work with him. Okay, so what I mean, I think I wrote in my abstract that I will give a general introduction in the subject, and well, what that could mean is many things. What I really meant is I'm going to really define everything that is supposed to enter this conjecture, because otherwise the main players of the conjecture do not make sense. But what I'm really interested in is I want to study C, which is some category where one can do homotopy theory. So that's basically the basic objects. Now, there are many things we can mean by this, but first of all, let's immediately say what's the first example you want to think about. You can do C to be top, which is sort of the category of topological spaces, where classically a homotopy theory is done. The topological spaces, and then we have all these notions here. We have a notion of homotopy, if you want, between topological spaces, which is or maybe I'll write it like that if you want, something like this. And more notably, and then you can form here some constructions, which is what is the homotopy theory usually doing? Well, like for example, we can also consider top star, which is sort of pointed topological spaces. Pointed topological spaces. Well, that's a topological space with a base point, for example. Well, mostly everything will be at least pointed in this talk, if not even stable, but I always have some topological space together with a distinguished point like that. And then, for example, one of the standard things you can form is a suspension of a topological space, which, well, in the picture, what it is, you have here a topological space, and then you do this here, the base point, and then you do this like cone on top and the cone on the bottom. So that's a typical thing you do in the topology to study topological spaces in homotopy theory, but you can also do its adjoint, which is the loop space. So it's just the loop space. And so these are the standard players you use in homotopy theory in topological spaces. And what I really want is not study topological spaces, but a category. Well, I will give examples of such categories where all these kind of things also make sense. It doesn't have to be necessarily topological spaces. For example, C can be the category of chain complexes over ring R, for example, like chain complexes. And all these homotopical notions also make sense in this category. Or, for example, C can be the category of spectra, which I will later mention again, but it can be SP, which is the category of spectra, which is the so-called category where stable homotopy theory takes place. Okay, so now what is the official definition of this C? Well, these are the examples you should maybe think of, but well, C in this talk is either a stable model category, which is axiomatization of this kind of homotopy theoretical approach I was talking about, or it's something which is more suitable to this talk, is called stable infinity category. These are two equivalent sort of ways of dealing with abstract homotopy theory in algebraic topology. So axiomatizing basically things I was talking about before. Okay, but now, well, we want to study such things. So study such things. Study means understand such things, because understanding the category of topological spaces or understanding the category of spectra, even chain complexes, is not an easy thing. I mean, how do you want to actually compute homotopy classes of maps between different objects and so on? So the typical thing you study is sort of mapping spaces, maps between X and Y. or homotopy classes of maps between X and Y. And this is a difficult thing to study. Okay, well, one of the best ways to do something like this in topology is, well, for example, you can consider singular homology. So what you can consider homology theories, like this is a usual singular homology going into abelian groups. So AB denotes the category of abelian groups. So this is a homology theory. So this is a homology theory. And most of the people in the audience, I'm sure, have seen what's singular homology. I'm taking advantage of the fact that we are here in algebra and topology and related topics seminar. Well, I mean, you all seen like singular homology of topological spaces. It's not an easy thing to compute, but it's quite a computable thing. For example, we know quite well what are homologies of spheres, for example. These are well known. I don't want to write it out. Okay, so homology theories are the basic tool to study such categories. And here is a general definition I want to give. So first of all, in this talk, A always will be an abelian category. If you do not know what's abelian category, think of abelian groups, the category of abelian groups or R modules. So typical example of A is R mod or abelian groups. Or even a vector space if you want. Actually, some places in this talk, I will mention examples where it will be just vector spaces or FP, for example. Abelian category with enough injectives. Well, there are some reasons why I prefer injectives to projectives in this talk. Reason is that at some point I want to get to comodules, and then comodules have enough injectives and not enough projectives. There is an auto-equivalence on this category, shift. To be really honest, a prototypical example of this A should be some kind of graded modules, and therefore I want to have some kind of a shift. There is some auto-equivalence here already given, auto-equivalence. So in particular, there is a minus first shift as well. And then what is a homology theory? So I want to define for you what's a homology theory. Homology theory on C with values in A. This is just axiomatizing in some ways what it is to have, like, say, Eilenberg-Steenrod axioms for singular homology or something like that. Okay, so what's a homology theory? The first thing is that it's a functor, of course, H from C to A, such a functor. It's a functor. Second of all, H is additive. So that means that it sends finite sums to finite sums. Well, this is a category where homotopy theory sort of makes sense. So in particular, you have wedge products if you want to ask what is a sum in C. And the third one is that well, first of all, I should mention maybe, well, this is not the axioms of homology theory, but maybe I should say that here I always mean C is stable now, which means that just to clarify once and for all, the suspension functor going from C to C is an equivalence. So in particular, it makes sense to talk about mapping cone sequences. So mapping cones make sense in mapping cone sequences. Or maybe some people prefer terminology cofiber sequences. Sequences make sense. Makes sense in C. And for any such mapping cone sequence, C, D, E, let's say, such a cofiber sequence or cone sequence, I'm asking that this homology stays exact. So if you have this kind of a mapping cone sequence, then you apply homology to it. Well, this is an exact sequence. This is exact. You can think of this as, well, both as an analog of some sort of excision type thing, as well as analog of the long exact sequence in homology, because, well, it's very general thing what you mean by mapping cone sequence, and that includes in particular the excision type statements. Okay, and finally, the fourth one is the commuting with suspensions. So if I take homology of suspension, well, you know probably from algebraic topology that should just shift homology. And this is why I fixed this autoequivalence from the beginning to tell you what's the homology of the suspension, and that is just homology and then shift. Okay, so if you have never seen anything like this before, then probably you would struggle. But I think in this audience, everyone has at some point seen in their lives what's a singular homology, and therefore this should be familiar. Okay, so now you might ask yourself, where is this homotopy axiom? Like usually when you have homology theory, you ask that if you have two homotopic maps, then they have the same value on homology. Well, that is encoded with the fact that C is actually infinity category or model category. So C is a stable infinity category, and A is a one category. And hiddenly, when I'm telling you, it's really a one category. I mean, I never said that it's some fancy version of abelian category, it's just a usual abelian category. So therefore, any functor like this factors through something which is the homotopy category of C. And that is basically this, the way I formulated it has a consequence, that actually the homotopy axiom is also satisfied. So you can think of this H either as a functor on C or as a functor on the homotopy category, which is now a one category, usual category HC. This is a homotopy category. Of C. And well, that is just a usual one category. Objects of HC is the same as objects of C. So objects do not change. Like when you do usual homotopy category of topological spaces, objects also do not change. But what are the morphisms in here? Well, morphisms are homotopy classes of maps. I told you in C I can do homotopy theory. I have notion of homotopy. So I can do homotopy classes of maps from X to Y in C, which by the way is the same as pi 0 of the mapping space inside X and Y, where pi 0 is the components. Okay, so so either you can talk about homology theories on C or homology theories on HC, and the axioms guarantee that these are pretty much the same things. Here, just a comment that, I mean, I'm not really going to use this in this talk, but this is also because the reason, if you do not know what this really is, the equivalent way of formulating this is that you take C, you take its homotopy category, and this is a triangulated category. So if you like the triangulated categories more, that's basically the analog of stable infinity category. But I don't want to go into that because that's another technical term, and I'm not really interested in introducing even more technical players in this talk. Okay, so now goal is study C via this. Well, then the first question is this good enough? Is H good enough? Well, in general, of course, it's not good enough. But my goal is to put some conditions on this H, slowly introduce some more and more conditions on this H that will guarantee that you can actually recover C from H. And well, that the idea itself maybe goes to Adams or even earlier, anyone that was trying to recover space by singular homology or cohomology. But the basic idea that you can actually recover lots of things about C from some reasonable homology theory goes back to Adams when he introduced Adams spectral sequence. And I will mention Adams spectral sequence later in this talk. Okay, so well, here is another definition, what it means to be good enough. Let's start saying what this good enough really means. Well, a homology theory like this is called adapted. And that's a place where probably I would have trouble to say what it is in Georgian, which is of course a shame, and I should know what this word really, how to translate this word well in Georgian, but probably I would struggle at that point. This topology theory
there's no need to translate it, just the same word, right? Or not?
Yeah. Adaptirably, I don't know.
I know just
Well, if anyone has a good term, please let me know. This is called adapted if for every, well, What are the good things in A? The good things in A are injectives. Like I told you, it has enough injectives. So at least maybe we should hit injectives. So it's called adapted if for every injective. By the way, lots of examples will come very, very soon. I'm just trying now to get into the general theory as soon as possible. So this is called adapted if for every injective I, there exists some object I see in C such that two things hold. Well, this is a bit of a, this is maybe not the most optimal definition, but for the talk purposes, I think it's a good definition. First of all, it realizes this I. So every injective has something here that whose homology it is, which in general might not be true. It's not like every object here has to be homology of something. And second of all, if I look at homotopy classes of maps from some C into this injective realization, and then I apply homology to it, well, where does that go? That goes to hom in here from HC to HIC. Well, what is that? Well, this is isomorphic to hom HC maps into I, as I told you, because HIC is isomorphic to I. I'm asking that this is also an isomorphism. So maps into injectives, into injective lifts inside C should be completely describable in terms of algebra. So that's the condition that you use to call the homology theory adapted. And in a second, I will give you many examples of such adapted homology theories. And the second, another condition I want to ask is that H is conservative. So H is conservative by definition if homology vanishing implies that the object itself is vanishing inside C. So that's good enough for me. So good enough, I had to give some conditions here on H, otherwise there is no dream even that I can ever recover C from A. And these are the conditions. It's really well behaved with respect to injectives, and it does see being zero. So it reflects isomorphisms or equivalences, let's say, homotopy equivalences in C. And that is already pretty strong condition to ask, but you will be surprised. There are lots of homology theories and interesting Cs where this is satisfied. For example, well, singular homology is not such an example, but if you look at simply connected spaces, for example, then singular homology is such an example. If singular homology of a simply connected space vanishes, then the space itself vanishes. The space is a point. So that's a famous fact. So there are examples of conservative homology theories. Okay, so this is a general setup. Now, what about A? So how good? What about A? How good should be A? What about A? What do I want from A? Well, I already asked. It has enough injectives. It has enough injectives. But I also do not want to deal with some infinite dimensional homological algebra here. So because of this, I will remind you, well, I mean, I should not explain homological algebra, I think, in this audience for sure. But I will just recall what's a homological dimension of A. Well, this is a maximum, let's say here, maximum, sorry. I need to delete this. I need to delete this because I forgot to write maximum. So homological dimension of A is a maximum of those M's such that there exists some little a and little b in A such that X does not vanish. Also, you can think of it as a minimal length of injective resolutions if you want inside A. So that's the homological dimension of A, and so what I really want to ask is the setup in this talk always will be, well, H from C to A, conservative, adapted homology theory with enough injectives, because otherwise all these notions do not make sense. Enough injectives, and homological dimension of A finite. A finite. So this is like the basic setup for this talk. And I mean, when I said introduction to the subject, I mean, well, I mean, I could have said more about these things, but I at least had to introduce all the players I'm dealing with, and these are all the things. Well, now what's good about this kind of setup? Well, this kind of setup immediately gives you something called Adams spectral sequence, and I will say a bit more words about history of this Adams spectral sequence. So this is an easy version of Adams spectral sequence where the convergence is not an issue and you have the best possible Adams spectral sequence you can ever hope for. So, or some people maybe in this audience will actually tell me that this is the universal coefficient spectral sequence, and they will be right as well, because universal coefficient spectral sequence and Adams spectral sequence are the same spectral sequence basically. But well, we like to call in homotopy theory these things Adams spectral sequence. So this is how it looks like. It looks like this. It starts with the X groups in the abelian category you work with, HC, HD, and some shift of that HD. Like we have this shift. I just remind you that we had this shift in this abelian category, so we can iterate these shifts if we want. So there is a higher shifts here. And that converges to homotopy classes of maps from C to, well, depending on how you grade your spectral sequences. I think I'm just going to grade it with a Serre grading in this talk and not do much of spectral sequences anyways. So this is the Adams spectral sequence that computes homotopy classes of maps from C to appropriate suspensions of T in terms of X in this abelian category. And well, I almost fulfilled my goal now in this talk. I was telling you I want to recover C from A and H, and well, this is the Adams spectral sequence that does recover it. But well, that's just theoretical. I mean, this spectral sequence can be very complicated in general, right? Very complicated in general. And there is no way you can say anything about C just from the spectral sequence because it can be huge and lots of differentials and so on. Well, let's look at the example before I give you examples where my discussion here applies. Let's look at example where it's more complicated even to look at the spectral sequence. Well, one of the good examples of homology theory, well, we can take C to be, well, we could take C to be spaces again, like finite CW complexes, but let's take C to be SP, the category of spectra. Well, if you do not know what spectra are, think of it as, well, collection of a topological space together with its higher and higher suspensions. I think that's a good analogy to think of as a spectrum if you do not know spectra. So this is basically a stable version of topological spaces. Well, and what you can consider on spectra, you can consider the singular homology with FP coefficients. And go to FP modules or FP vector spaces. Now that's a good old vector spaces over finite field, whatever abelian category was in my talk. This is the easiest abelian category you can maybe look at. Well, this is conservative homology theory if you introduce here some completions and things like this, but let's not talk about completions. So let's not bug ourselves about conservativity, but this is not adapted, for example. It's not adapted. So for example, it does realize injectives, but maps in spectra into the things that are kind of injective are not seen by FP vector spaces. But a thing you can always do, you can factor this over something called comodules over a lower star. And this is the dual Steenrod algebra. This is the dual Steenrod algebra. Dual Steenrod algebra. Well, this is something like, well, you have some homology theory, and well, just as a vector space, it's not good enough. So you add all the extra stuff that is in there. For example, you add all the homology cooperations, or if you like cohomology, you could also add all the cohomology operations. And well, there is a forgetful functor here, of course. This is more stuff than just vector space. And if you look at singular homology with coefficients into the comodules over the dual Steenrod algebra, then this is an adapted homology theory. So this is adapted. It is adapted. So it does realize injective comodules. And that's the reason why I'm talking about injectives, because I actually want to look at even more complicated comodules later. It's adapted, and well, there is also an Adams spectral sequence, classical Adams spectral sequence. Adams spectral sequence. well, even though I do not need this in my talk, I will tell you how this is used. There is, for example, atom spectral sequence for computing stable homotopy groups of spheres, which is one of the most complicated problems in algebraic topology, stable homotopy groups of spheres. Well, maybe that I have a job is because of this, that stable homotopy groups of spheres are hard to compute. Otherwise, any of the things I'm talking about is useless. So even though I have never computed any new stable homotopy groups of spheres in my life, I mean, the reason why all this stable homotopy theory is interesting is exactly trying to do this. And so there is an atom spectral sequence, a classical one, which is x over of comodules over the dual steno algebra, FP, FP. Well, it's mostly interesting at prime 2, this kind of spectral sequence, because otherwise you should go to Adams-Novikov. And that goes to stable homotopy groups of spheres. So it does go to, pi t minus s. And then I will make here this little sign p, though this, you should ignore this, just like does something in degree 0, and otherwise it's just usual stable homotopy groups of spheres. And lots of things have been calculated using this, at least in the case when p is equal to 2 is especially important. Well, let me make a little table here, how complicated these homotopy groups of spheres are, just to show you why this atom spectral sequence is so important. That, well, after certain stage, it's just impossible to do anything without really digging into this atom spectral sequence, and this is why it's sort of important to study this kind of spectral sequence. Well, let's say k here and pi k here, and then we have 0, 1, 2, 3, 4, 5, 6, 7, maybe let's go 8. And then I don't remember anymore. I used to remember it until 16, but well, I'm also getting slowly older and forgetting all this stuff. So here you got Z. Here it's Z mod 2. That's the Hopf map, first Hopf map. Here you have Z mod 2, that's the Hopf map squared. Here you have Z mod 24, and that's the next Hopf map, the quaternion Hopf map. Here it's 0, it's 0. These are really remarkable why these things are 0. I mean, I always wondered this my entire life, and I cannot explain this except, again, look at some minimal resolution or something like this, or steno algebra. This is Z mod 2. This is, I think, Z mod 240, if I remember correctly. Well, already you see, I might be forgetting, but already some huge numbers show up very early. This is the next Hopf map. I think it's the octonion Hopf map. And then there are no Hopf maps like this after this. I think this is Z mod 2 to the squared, that one. And then I forgot. At some point I remembered it until 16, because that's where the first differential actually shows up in the atom spectral sequence. That's the 16th one. Well, I'm not going to really use any of this stuff, but just to show you that homotopy groups of spheres are super complicated, and atom spectral sequence is a great tool to compute it. And for me, I'm going to use atom spectral sequence, but in easy situations. For me now, the goal is to find some conditions. Well, we have this atom spectral sequence in our setting, which is a bit less scary than, I think, the homotopy groups of spheres atom spectral sequence, because I already assumed that my abelian category was finite dimensional, and that already makes a huge difference. Sorry, I made a mistake here. I need to correct it. So it's ES, T2, and this spectral sequence I wrote you is looking like that. So this is the atom spectral sequence in my setting for this homology theory HC. And so what I really want is not really study complicated versions of the spectral sequence, but impose even more conditions to ensure to see that in some cases, it just collapses. It collapses. And if it collapses in good enough cases, then there is even more hope that you can recover C out of this H of this homology theory. And so what are the cases when this will immediately collapse? The first tautological case, of course, is when HD is injective. HD injective guarantees that this spectral sequence immediately collapses, and there's nothing to worry about here. Well, why? Because the higher X groups immediately vanish, if you stick in the second variable in injective object. But the second condition is that, well, and that is something I should define for you, HC and HDT sort of are far away from each other, far away from each other. And that is intentionally put here in this quotation marks because I need to define what that really means for us. But the idea is if they are too far away from each other, there are no extensions between them. And you can imagine how something like this could work in graded setting, for example. If you have some graded module concentrated in some degree and some other graded module which is concentrated super far away somewhere, maybe there is a mismatch and you cannot have an extension between them. Well, here is a precise definition of the kind of explanation what this far away really means. Here is a precise definition. So a splitting, this is the time, a splitting of order q plus 1 of A of the abelian category A is a Serre subcategory, and I will explain what that is. Serre subcategory B inside A. Well, I think in this audience there are people who know this definition, remember this definition probably better than I do, but well, I basically mean full abelian subcategory, so everything is inside kernels, co-kernels, exact sequences, abelian subcategory, together with extension closed, so it's extension closed. So that's, I think, all I'm asking. So a splitting of order q plus 1 is a Serre subcategory B such that what you can do, well, this abelian category always comes with this shift I told you. So you can look at B, you can look at shift of B. Well, you can look at the second shift of B. You can keep on shifting this stuff until you get B to the Q. That's where this Q comes in. And you can map all of these things to A. So by taking here B0, take here B1, take here B2, and so on, take here BQ, and map this down to the direct sum, B2, and so on, BQ. So I'm basically asking for some weight structure. So I'm asking that there is some direct sum decompositions, and I'm asking this to be an equivalence. So this is an equivalence. So I want A to split. A good example, for example, of such a splitting would be if you consider, for example, A to be, say, graded modules over some even ring or something. Then you can divide things between even and odd parts, like typical super grading kind of thing in mathematical physics is, I think, also this kind of structure. Like it's a weight structure, like even and odd, but you can actually have more stuff. Well, I hope that in 5 minutes I'll get to examples. So I will give you a lot of examples of this kind of.
Can I ask a quick question?
Yeah.
So there's no other condition on B just being set subcategory?
It's just a Serre subcategory, yes.
So it can be A itself.
It can be what?
A itself.
It can be also A itself, yes. But
and then you get, so what condition does it mean then?
Then it's an empty condition. So you better, I mean, of course you can say it's Q greater or equal than 0 here. Well, you can ask for that. Well, when Q is 0, it's boring. It's nothing interesting. So more interesting situations are when Q is positive. But yeah, formally speaking, yes, Q can be 0, but that is then an empty condition. There's nothing there. But I'm asking, well, later I'm going to ask that Q is large enough. In my condition, I will ask that there exists large enough Q doing something. And there, of course, this will be a serious condition. Let's wait for the conjecture, and the conjecture will say that Q has to be bigger than cohomological dimension of A. And then it's going to impose a big condition. Yeah. So typical example, let's already mention this then, like interesting case is, well, I should mention this because then it actually collapses the Adams spectral sequence. So interesting case, but it's a good question because otherwise, I mean, it's boring, right? I mean, I take Q is equal to 0. Interesting case is when the cohomological dimension of A, let's say, is less than Q plus 1. So in particular, if A is vector spaces, for example, then I can take Q is equal to 0. And that would still do the job. But then again, this Adams spectral sequence in that situation is boring because then there is no higher X groups anyways. But if you give me more higher cohomological dimension categories, then I should better have this Q bigger than this. And in this situation, if I take any of these HCs in one of these BIs, and I take any of these HDs in one of the BJs, and they don't even have to be different, this I and J, then the Adams spectral sequence collapses. So then this Adams spectral sequence collapses. Collapses, I mean, it degenerates completely in the sense of it's only one row you're going to have, or one column now. I don't remember which one is which one, but Adams spectral sequence collapses. And so this is what I will be interested in this talk. So large enough Qs so that this happens. So this Adams spectral sequence not always collapses, but if HC and HD are in these different weights and the homological dimension is smaller than Q plus 1, then it will collapse. And so therefore, I should suspect that in this situation, there is even more to say. Okay, so now before the conjecture, let me give you some examples of these examples. Then I will formulate conjecture, and then I will give you even more conjecture or theorem, even more examples. So examples, the first one is the tautological example. Well, are there even any examples of such homology theories, you can ask? And there is the tautological example. But before that, maybe first of all, I should ask Soso if this did answer his question. Did this answer your question? I mean, should I say more maybe about? Yeah. Anybody else maybe has questions?
Yeah, you did.
Okay, thanks. Should I say something more? I mean, as anybody has now, maybe it's a good moment to ask a question, because now I'm going to formulate the conjecture and then give you the applications and concrete examples. Because I think I did know enough of the theory somehow to be able to say things.
Just a quick comment. So adaptive, maybe it could be misadagებული.
Ah, that's a good word. Yeah. That's a good word. Yeah. Nice. Okay, seems like no questions, so I can just give you a tautological example. So I want to just start with a abelian category. Abelian category. Again, enough injectives. And let's say dimension finite, even though even that is not really needed in this situation. Well, you might ask yourself, is there even a homology theory always taking values in here? And the answer is yes, there is. What you can consider, well, I have also this autoequivalence. So what I want to consider is basically chain complexes, but chain complexes which take this autoequivalence into account. So here is a definition: a differential object in A is something you probably all have seen what it is. It's some pair A comma this partial del that goes from A to A shift and such that it squares to 0. Well, squaring to 0 should be understood in the following way. Because of this autoequivalence, you can think of this thing as some sort of a chain complex, a periodic chain complex. So it's not really a chain complex because I have to take this autoequivalence into account. And it's not the chain complex shift as well. It's the autoequivalence. It's sort of the chain complexes of graded modules somehow, if you really want to think about example. So you can think of it like this. This kind of like a long sequence. And what I'm asking is that this is a chain complex, basically. That's the condition. So that's what I want to call a differential object with respect to this A and this shift. Okay, so it's a chain complex. And this is how you should think of this differential object, actually, in a periodic chain complex. So in particular, what you can say is that what it's homology. So homology of this differential object is actually degree 0 homology of this chain complex. Is sort of the kernel of delta modulo the image of delta minus 1. Okay, good. So now what I can define for you is that f from some A to AD to B delta map of differential objects is a quasi-isomorphism or homology isomorphism if it induces isomorphism on homology. HF from HA del to HB delta is an isomorphism. So I introduced this notion of quasi-isomorphism of these differential objects, and now this is this good old derived category construction, though it's a bit different here because it takes into account this autoequivalence and it's sort of some sort of a periodic derived category if you want. So D per A, this shift maybe, or I just will denote it by D per A. It's just the differential objects. You take the category of differential objects. And what you do with this thing, you invert these quasi-isos. So you localize it quasi-isomorphisms. Well, this is inverting quasi-isomorphisms. Well, again, in which world do you work in? If you work in the world of triangulated categories, you localize this in the sense of triangulated categories, but I work in stable infinity categories, so I'm actually localizing here in the world of stable infinity categories. And this homology now becomes a homology theory on this perfect derived category. So you have this H going from here. Well, objects again here are usual differential complexes. It's just the morphisms have changed. And why did I localize it quasi-isomorphisms? Because I want this homology, this homology I defined here for you to be adapted. So I want it to be also conservative. I want it to sort of reflect equivalences. So if I wouldn't invert quasi-isomorphisms, so those morphisms that are seen as isomorphisms by H, then of course it would not be conservative, for example. Now, fact is that this is adapted homology theory. So basically for every A, I was able for you to construct a tautological example using chain complexes in A and using the usual homology of chain complexes as an example. And so such example is always there. And now what this Franke's conjecture really says, well, informally, and then I will also formulate it formally, Franke's conjecture really says is that every good enough, every adapted homology theory under this kind of under certain conditions. Well, what that is, I will describe it. Is very much related to the condition we already discussed about collapsing of atom spectral sequence. Under certain condition, every adapted homology theory is the tautological one. And this is a big statement because you are saying that in particular, you are saying that in some ways C is equivalent to this perfect derived category, but it's not quite equivalent. It turns out it's not equivalent, but well, at least the homotopy categories are, and we will say this. Okay, so now official formulation of Franke's conjecture. And then after that, I will give you examples and applications where this applies. I still have, I think, 15 minutes, so I think I'm doing okay with the time.
Plenty of time, just yeah.
Thank you. So definition, just to recall what these things are. So if C is this kind of infinity category, so if C is an infinity category or model category, infinity category or model category. Then we do not necessarily only have homotopy classes of maps, but we even have like mapping spaces between objects. That's the whole fun about homotopy theory. So homotopy theory as such does not really exist if you do not have mapping spaces. And if you truncate these mapping spaces to homotopy classes, then you are actually not looking at the full structure of homotopy theory. And I mean, there are some people in this audience I know have thought a lot about things like obstruction theory, for example. And so now what I really want to look at is some sort of obstruction theory for these mapping spaces. Well, this is just a mapping space. Well, if you want to think about what is a good analogy of this thing, well, think about topological spaces together with compact open topology mapping space. That is a good example of such mapping spaces. And then what you want to define is the homotopy N category. H and C is the homotopy N category. Homotopy N category. Well, this is not an N category in terms of technical term of like higher N categories in the sense of like, well, it is equivalent to that, but it's much easier here to formulate. So homotopy N category here means objects of C, objects of H and C are the same as of C. Well, objects do not change again, but mapping spaces in this H and C, well, technically speaking, you have to work a bit more to define this homotopy N category, but I'm just telling you the content, what it is. Mapping spaces in here are just the Postnikov truncations. So mapping spaces in here are the Postnikov truncations of the mapping spaces in C. So it's n-1 truncated Postnikov sections of this X. So it's n-1 truncated. Postnikov section. So that's what it is. So this homotopy N category sees the same objects, but it truncates the mapping spaces. In particular, homotopy 1 category is the homotopy category of C, the usual homotopy category of C. It's the usual homotopy category. Because zero truncation of mapping spaces is the homotopy classes of maps between the objects. Usual homotopy category. It's the pi zero, basically. Okay, so now we are ready to formulate the Franke's conjecture after I introduced all these players. It turns out that I need these truncations of homotopy categories to actually tell you the optimal statement. Here is a theorem. And I will tell you also some history of this theorem in a second. So this is Franke's algebraicity conjecture. Algebraicity conjecture, which originally was actually a claim, a theorem, but well, it turned out that he was wrong at the beginning. So this is a theorem proved by myself and Piotr. All right, so theorem says the following. So suppose H from C to A. Well, maybe I should write also year here. It's from 1996. Okay, so H from C to A is an adapted homology theory. Adapted homology theory. Homology theory. A has enough injectives. I should not forget all the conditions, enough injectives. Finite dimensional. Well, that is probably guaranteed from the next thing I will say, but let's put this down. It's adaptive homology theory, finite dimensional. H is conservative. So the atom spectral sequence makes sense. Otherwise, you have to argue about convergence. Suppose A has splitting of order q+1 has B splitting, like that splitting I was talking about before. So where is this splitting? Yeah, the one Soso asked the question about as well. So this shares subcategory kind of thing. And the main condition, which we already mentioned there, that was good that we got this question, and also assume that the dimension of A is less than q+1. So basically, these are conditions before I formulate the result. I have this homology theory. There are enough conditions so that there is an atom spectral sequence, basically. And I'm also asking that sometimes this atom spectral sequence collapses if I have far enough from each other objects. And that's sort of basically what this condition says. And this condition, of course, guarantees that collapse in this situation. Otherwise, this would be impossible. Then what we know is that homotopy q+1 minus, well, let's call this D to abbreviate the notation. Homotopy q+1 minus D a category of C is equivalent to homotopy Q plus 1 minus D category of the tautological example. So this site has nothing to do with the topology or anything anymore. So this is purely homological algebra, it's chain complexes. Whereas here it's the C, and this C can be anything. This C can be anything, absolutely anything. As far as you give me the homology theory, it turns out that C is in some ways equivalent to the chain complexes. But now you may ask, well, this was the Franke's conjecture, and of course the idea is what I just said. There is Adam spectral sequence, and in many cases it collapses, and it's good enough to actually recover C out of this. Now there are several comments before I say examples and applications about this. So first of all, Franke claimed this this result in '96 in his paper, or a version of this result, because what we prove here is actually stronger than what he claimed there, because this is a consequence of this stuff what we prove here. But you can argue that this is also in some ways equivalent to what he formulated and not stronger. He formulated this thing in '96. He wrote this preprint. He was encouraged by many people to write this preprint because around that time there were lots of ideas concerning this stuff, including Bausfeld was writing some papers before that about this kind of stuff. And Franke wrote this paper, and then in 2008 there was a mistake found in this paper. One of the main parts of the proof contained an error which was not possible to fix for many years afterwards. And that error is still not fixed. I mean, nobody knows if that is possible or not. And I suspect it's a very difficult task to fix that, because I have worked many years to try to fix that thing, and many other people have tried. We all failed. But then sort of, well, I have to give here credits to Piotr. Piotr wrote his thesis about a special case of this stuff and came up with some new ideas about what one could do to maybe try to actually prove this claim in a completely different way. And then we started to talk, and then eventually we joined forces and proved this theorem. So interesting thing here is that we also talked to Franke about this, and he was happy to actually now call this his conjecture, because well, around 12 years ago I had well, even longer ago, 13 years ago now, I had some conversations with him, try to fix that thing, and eventually he agreed that there was a problem there. And when we sent him this paper, he was very happy and saying that yeah, feel free to use this name for calling the statement like that. So in that sense, we also owe a lot of credits to this guy Jens Franke for his ideas, and well, he's originally the person who looked at this conjecture at all. Okay, so now what about some comments here? First of all, this number here is optimal. So comment here, remark, this thing is optimal in the sense of like you cannot go one up. A good example for that, and this is maybe the moment when I should start talking about examples anyways, you can take, for example, C2B modules over something called Morava K theory. I don't know if Malchaz is around, but if he's around, then he's an expert in Georgia of this kind of Morava K theory kind of stuff. So this is Ent Morava K theory. Ent Morava K theory. And so why is this interesting? What is the corresponding abelian category? The corresponding abelian category in this case is modules over graded modules. Let's call it pi star kn, modules over this thing, the kn modules. So it's graded modules over this. Well, what is this pi star kn? It's a Laurent algebra. The Laurent algebra on FP. Let's call it like that. And this is the degree. It has degree 2pn minus 1. Okay, so it's optimal in the sense that, like, it turns out that in this case, well, what turns out is that in this case, well, homological dimension of this category, D, so dimension of A, or cohomological dimension if you want, is 0, because this is a graded field. It's basically vector spaces here we are talking about. But the splitting is exactly this number. So Q plus 1 is equal to this this number, to Pn minus 1. Well, I will talk more about the splitting in a second. But what I want to immediately say is that in this case, homotopy 2Pn minus 1 categories are equivalent of this and of the periodic complexes over actually this d per of this A are equivalent. Well, A is this in this case. They are equivalent, but if you go up to one up, if you go one up, they are not equivalent anymore. They're not equivalent. So I don't want to write it out now, but you know what I mean. If you just go one up, they are not equivalent anymore. And that's just a classical obstruction theory with mapping spaces. It tells you that some mapping space on the algebraic, on the non-algebraic side is not product of Eilenberg-MacLane spaces. And that goes back to some element in dual sternode algebra, which is this Milner's primitive Qn, but let's not discuss this. So what I'm telling you is optimal in the sense that you cannot even make one more this thing. You cannot get any better than this number here in general, what I formulated. So in particular, in all the examples, what I'm really telling you, C is never really equivalent to this periodic derived category. All the examples I will mention. It's only after enough truncations of mapping spaces that it actually becomes equivalent. Okay, so now applications and examples. Well, first example is something I have worked many years on, and I really like this example. So you can start R being any sort of U1 ring or a differential graded algebra if you want. So even a differential graded algebra would do the job here. Differential graded algebra. And what you can assume is that its homology or homotopy ring, is sort of, well, that's just a graded ring. And what's a good example of adapted homology theory? Well, you can look at modules over this R. Well, it's something you really seriously studied in a stable homotopy theory, and you can look at its homotopy groups, and that lands into the graded modules over this pi star. So this is a good conservative adapted homology theory. Conservative adapted homology theory. Adapted homology. So in particular, for example, S modules, when S is a sphere spectrum, just to comment here, S modules is the same as spectra I was talking about before, SP. So studying these modules is very important because, well, studying modules over the unit is just usual spectra, and that is related to homotopy groups of spheres. Well, I know I'm almost out of time, but I will take another 5 minutes to give you all the examples.
Yeah, 5 more minutes.
Yeah, thank you. So, and what I want to ask here, a condition is that, well, how do I guarantee these splittings and dimensions? So first of all, I want to ask that injective dimension or global dimension of this ring, which is in this case also the same as projective dimension in all the examples, at least I'm considering. I want to ask that this dimension is finite as a ring, so injective dimension. Well, sometimes this can be also described as a Kroll dimension. And the other thing I want to ask is that pi nr, so there exists some number q such that pi nr is 0 unless n is congruent to 0 modulo q plus 1. So I want the homotopy ring only to be concentrated in degrees divisible by this q plus 1, which was the case, for example, for this Morava K theory. The q plus 1 was exactly this, and everything was concentrated in degrees divisible by this thing. Well, we will mention more examples of this, but let's assume also that this cohomological dimension, again, is less than this q plus 1. And then what is B? So a graded module is inside this B. Again, if and only if, well, let's call this M star, if and only if Mn is 0, unless n is congruent to 0 mod q plus 1. So basically, when I have a ring where the elements are only concentrated in graded degrees divisible by something, you can split up every graded module as things concentrated in degrees divisible by this number, divisible by +1, +2, and so on. And then you come back. So basically you are sort of graded over Z mod q plus 1 in this case. So that's where the splittings come from. It's sort of the kind of a weight decomposition in this situation. Okay, so, and if you have such a thing, then the theorem implies that homotopy and homotopy, let's call this D Q plus 1 minus D category of R modules. Well, what are the periodic complexes in the case of graded modules? Well, shift in this case is just, well, I should maybe tell you what's the shift here. There is this shift here. Well, this is the usual graded module shift. And if you take that into account, then it turns out that this is the same as homotopy Q plus 1 minus D category of differential graded modules. Differential graded modules. Well, this periodic category is explicit in this case, differential graded modules over pi star R. So it's a purely algebraic sort of category on this side, and this is the modules over this ring spectra. And things to which this applies are a lot of things, actually. So, for example, well, KU, complex K theory, real K theory at an odd prime is a good example. For even primes, it's for prime 2, it's not possible to apply, so P odd, connective. There are these Brown-Peterson spectra, which you can apply this to. And here the condition is that m plus 1 is less than 2p minus 1. The Johnson-Wilson theories, En. So this is the Johnson-Wilson spectra. Johnson-Wilson theories. And here it's n less than 2p minus 1. So that's the typical example where this module business applies. And now, what about the most important example where Franke was actually looking at why Franke was even looking at all this stuff? So main example here is the example that is useful in the chromatic stable homotopy theory. So, well, I mentioned for you this Johnson-Wilson theory. So anyway, so this is a case when R is En. This is some spectrum, and its homology, its homotopy groups, are the same as something like this. C localized at P. It's a polynomial algebra in n variables, and then you invert the last one. Well, let's write here n minus 1, and then here plus minus 1. And each of these VIs lives in degree 2 pi minus 1. And what you can do is you can consider En local spectra, where these kind of objects are constructed in order to compute stable homotopy groups of spheres. So this is En local spectra. Bausul invented these things, local spectra, and it's a very difficult thing to study. If you study all of these at every prime, then you basically compute stable homotopy groups of spheres if you can understand these things. And there is a homology theory, which is a good homology theory here, which is En homology itself, going into so-called En star En comodules. And this is also an example of adapted homology theory and sort of dimension of this category. So D in this case is equal to n squared plus n. And periodicity, as you see, is equal to this Q is equal to p minus 1 again. So if you assume that this is less than 2p minus 1, so if you assume this, well, and this is a famous case when the atom spectral sequences in this setting collapse, then what you can conclude is that this homotopy n squared plus n minus 2p minus 1 categories, sorry, it's the opposite. It's the opposite. That's the last statement I will write, because this was the biggest application of this result. Homotopy 2p minus 1 category minus n squared minus n of this En local spectra. Well, that is equivalent to homotopy 2p minus 1 minus n squared minus n category of these periodic complexes of comodules. En star En commod. That was the original reason why Franke even looked at all this whole business, because that was the thing people were after. In particular, this generalizes results of Bau's field and when n is equal to 1. And one last comment I want to make. Recently, there was this paper by Tomer Schlank, Tobias Bartel, Ned Stapleton, and Tomer Schlank about some ultra product of these categories of SPEN and these comodules being equivalent. So ultra product means that you have some equivalence of these two categories, and you know that any statement that is true for large enough prime on one side is true for the large enough prime on the other side. Well, this result now implies this ultra product statement too, that the ultra product of these SPNs over some FP, which is this ultra filter in some ultra filter. I do not want to go into this stuff, but of these things, because this basically is the infinite limit prime. So this is the ultra filter in sort of you take the set of all prime numbers and you take a Stone-Check compactification, and then you take one ultra filter that is not the principal, and you take ultra product of these, and they are equivalent. But now we actually have a finite statement here, and that implies sort of this ultra product. And the other thing I have to say, and then I'm done, if you assume more, so if you assume the bound is worse, then this result was already proved in Piotr Strągowski's thesis. And that's where everything started from. He proved that result in this case, this concrete result in this case. And then it was kind of clear that some things he was doing was not quite as general, but then again, like some technology he developed there was general enough to actually come up with the proof of the more general result. And the reason why this new technology is slightly better than what he was doing in his thesis is that, well, it improved this bound. But he definitely deserves credits for writing his thesis about these things, and first being the one who actually even came up with the ideas that such a thing could be done. Now, I didn't have basically zero time to give a proof. The proof is very technical. If there are questions, I can just comment on the proofs and say maybe a few words. But anyways, yeah, thanks a lot, and sorry for going over time.
Thank you, sir. So thank you very much. It's nothing short of impressive, I guess, the result and technique, scope of the techniques involved here. I stop recording here.